Welcome to EDU World Space.
So when we're talking about orbital motion, we always want to talk about orbiting around an object, such as the sun, and that our orbit is an ellipse, right? This is kind of unfortunate just because it's not as easy as a circle, right? If we had a circular orbit, we could just kind of talk about the radius. We know the swing, we know the arcs, we know the area, we know the circumference. But that's not exactly the case with our ellipse, right? So we're going to need to define some other ways of talking about an ellipse, especially because we have our sun in the middle, right? The sun right here. So what I'm going to do is I am going to drop some imaginary lines, right? I'm going to cut our ellipse in half, kind of give it a nice little y-axis, right? And I'm going to draw a line through the ellipse, through our object, and give it an imaginary x-axis. Now, these are super important because although we only have to focus on our sun here, right? They're still super important because we need to talk about distances. So our distances that we really care about here are going to be the aphelion. The aphelion is the furthest point away from the sun, right? And then we also want to talk about this point over here, our perihelion, which is the closest part to the sun. So when we talk about our perihelion and our aphelion, notice how one we talk about exclusively on one side. So our perihelion is really just concerned about this distance right here. And our aphelion is concerned about this distance all the way over here. So if you think about it, perihelion and aphelion should kind of sum up to, this total distance of our ellipse. But you notice I haven't put any numbers on the screen yet. So let's go ahead and do that. So in order to kind of define a formula for perihelion and aphelion, let's imagine that this is kind of like a 0 point, right? This is our middle. So we can say that this distance right here and goes into the axis, and this distance over here is the same, right? We call it A, and that A is defined as our semi-major axis. Semi-major axis. Now, this is going to vary depending on the planets that you have, right? So Pluto is going to be different than Mars, is going to be different than Venus, etc., right? Additionally, you also have something called eccentricity. So eccentricity is defined as E, and that's going to be eccentricity. So that value actually defines how much of an ellipse you are, how elongated you are. So if you have a high eccentricity value, that means you are going to be very long. If you have a low eccentricity value, it means you're going to be closer to a circle. Once again, this is both defined by the planet that you are. So every planet will have a different semi-major axis and different value for eccentricity. Now, if we would like to define this distance further, let's go ahead and say that our A is 1, right? Oh, let me put that in a different color. So our A value will be 1. So there's a 1 on this side and a 1 on this side. I'm going to talk about it as though it's an absolute value. So we're not really going to add in any sign values to them. It's just 1, right? Now, if you look at this visually, especially for perihelion, you have perihelion, this distance in pink, right? This distance in pink is going to be a part of 1. So 1 is going to equal this perihelion. Let's name it P. And it's also going to be this residual distance, right? So P is going to be P plus this residual distance, and we're going to call that residual distance EA. Sound good? So once again, residual distance is going to be defined as EA. Now, if we rearrange this, right, so we want the definition for perihelion. So if we arrange it, it means that our perihelion will be equal to this one value, or this EA value, I should say. Let's do it the easy way. Or EA value minus that one value, right? And that one value, if you remember, is our A. These are the same thing. We're just making the math easier for ourselves. So if we were to rearrange this, right, our perihelion would be equal to our EA minus A. Because once again, 1 was our A value. If we factor this out, right, we're going to factor out our value over here, right? So perihelion is going to be equal to A times E minus 1. Right? If you do some fancy algebra and prove it to yourself, it could also be A 1 minus E, because once again, we are dealing with absolute values, right? So perihelion is equal to A 1 minus E. All right. So that was perihelion. What about aphelion? Well, aphelion is kind of a little more intuitive. This is because we are looking at this full distance, right? So we have 1 right here from aphelion to our center line, and we're going to add this EA value now, right? So our aphelion is going to be, once again, this one value over here plus that EA value. So these are two really important formulas that we're going to use moving on, right? Because once you know these two values, you'll be able to solve for perihelion, aphelion, and a few other things moving forward. So let's go ahead and take a look at a practical example of that. So a practical example of that, let's take a look at Pluto. So I'm going to erase this proof just so we have a little more room. All right. So I will rewrite these formulas as well. So the, once again, perihelion is going to be equal to our 1 minus E times A, and our aphelion is going to be equal to 1 plus E times A. Same proof. Okay, so if we're talking about Pluto, so Pluto has a semi-major axis that is 5.92 times 10 to the 12th meters. Okay, so that means that our A here is 5.92 times 10 to the 12th meters. The eccentricity for Pluto is going to be given as 0.248. Notice how eccentricity doesn't have any units. Little exclamation point. There's no units here. Okay. So if we wanted to find the perihelion for Pluto, so if we wanted to find the closest value for Pluto, so our perihelion to the sun, that's going to be our 1 minus E times A. So as we do that, we're going to set this up, plug in our values. So 1 minus 0.248 times our A value, which is 5.92 times 10 to the 12th meters. So when you plug that into your calculator, you should be getting, make sure that you're doing PEMDAS. So make sure you're doing this value first before you multiply in, right? So you should be getting something around 4.43 times 10 to the 12th. So that would be meters. Remember our units, So that would be the distance, once again, between the sun and Pluto when Pluto is at its closest point. So perihelion. When we talk about aphelion, let's use a different planet, just to kind of impress upon the point that our semi-major axis and our eccentricity is planet dependent, right? So if we talk about Neptune, so let's say we're finding the aphelion of Neptune. Once again, that's going to be 1 plus E and A. So our eccentricity for Neptune will be 0.01, and our semi-major axis for Neptune is going to be 4.5 times 10 to the 12. Okay, so once again, we're talking about aphelion. So it's this whole 1 value plus the EA, right? Cool. So it's going to be 1 plus 0.01 times 4.5 times 10 to the 12. So if you're comfortable, once again, make sure that you're following, the rules of our operations. So this is really just going to be 1.01 times 4.5 times 10 to the 12. And if you plug that in, you should be getting something along the lines of 4.54 times 10 to the 12. All right. So once again, this is how you get your perihelion. This is your aphelion. These are just also 2 really good equations to know for elliptical orbits. All right. So finally, let's go ahead and talk about time. So obviously, each planet is going to orbit around the sun at a different time, right? So let's go ahead and take a look at that. So do you want this eraser? All right. So when we're talking about time, obviously that is dependent on a planet's mass. It's dependent on its eccentricity. It's dependent on the semi-major axis that it has, right? Because if you have a shorter semi-major axis, that's going to be a shorter ellipse around your object. However, if you have a larger semi-major axis, obviously it's going to take you a longer time to orbit around an object. So once I get this stuff off, all right. So if we're talking about time, we are now going to talk about the period at which it takes to go around an object. So that equation is going to be T equals 2 pi semi-major axis to the 3/2 all over the square root of the gravitational constant times the mass of the sun. Now, you may remember this from Newton's gravitational equation, right? The only differences we have here is that we're using the mass of the sun because that is the object in question. I'll go ahead and emphasize him again. That's the object in question. And it's also going to take into account the semi-major axis because, once again, that's kind of the distance that we're talking about here, right? So I'll write this out again, just so it kind of helps you out. Once again, our A over here is our semi-major axis. Our G is our gravitational constant. And MS is our mass of the sun. If you are given a problem that requires a different star or is looking at a different orbit, obviously that will change. But our constants right now, so our gravitational constant, just as a heads up, is going to be 6.67 times 10 to the negative 11th. And that's going to be in newtons per meter squared, kilograms squared. Our mass of the sun, on the other hand, so I'll do it in orange because that's the color of our sun, So 1.99 times 10 to the 30th kilograms. Now that's a big number, but it kind of makes sense, right? The sun is pretty big. So when you have all of this information here, really the one thing that you're going to get from your planet is going to be the semi-major axis, right? So once again, for Pluto, so let's say Pluto A, that is going to be 5.92 times 10 to the 12th meters. Sound good? So once we have all of our variables here, right, we can kind of just plug it in. So we have our period, which is going to be in seconds, equal to 2 pi over our semi-major axis. So here it's going to be 5.92 times 10 to the 12th meters. And that's going to be to the 3/2. Okay, and then we are going to stick that over the square root of our gravitational constant. So that's going to be 6.67 times 10 to the -11th newtons per meter squared, kilograms squared, and multiply that with the mass of the sun. That's going to be 1.99 times 10 to the 30th kilograms. Notice how this is under a square root. So because it's under a square root, let me make sure I'm a small enough pen. Because it's under a square root, that's not going to matter anymore. These are all actually going to cancel out. And it will leave you with seconds once you go in and dissect that Newton unit, right? So when you plug this in, I like to do it in parts. So I'm going to put that down at the bottom. So when you plug this in, your numerator should kind of look like 9.05 times 10 to the 19th all over the square root of 1.327 times 10 to the 20th. If you simplify that again, you're going to get 7.8562 times 10 to the 9th seconds. Notice how this is in seconds. Typically, we don't talk about orbits in seconds, right? We're going to talk about orbits in years. So if we talk about it in years, we need to convert from seconds to years, right? I like to convert from seconds to minutes. So at that point, you have 60 seconds in 1 minute. You're going to knock out your units, right? So that's going to end up being 1.3093 minutes. And the reason I did that is because I remember minutes to years from that song from Rent. So I know that there are going to be 525,600 minutes in 1 year. And when I plug that in, I'm going to get approximately 249 years. So that being said, there's a lot that you can do with these equations, perihelion and aphelion. So once again, perihelion is going to be 1 minus E times A. Our aphelion is going to be 1 plus E times A. And then, of course, we have our gravitational equations and things that we can derive from that. So hopefully this gave you a better idea of what perihelion and aphelion are, as well as how we can use it to practically talk about things like period.